Okay, we'll look at some more examples of metrics, and these are in some sense more than metrics, they're ultrametrics. We'll see what that is along the way. Okay. So our first example is going to be a distance between infinite sequences. So let x be 0, 1 to the power of n. Okay, so this is just the set of all functions which will take alpha mapping, not 0, 1 but natural numbers, to the pair 0 and 1. Now there are, depending on the context, there are different ways in which you will define a distance on it, but the way in which we want to define a distance on this is thinking of this in terms of a tree. So suppose we have a path that goes this way or this way. So let's look at this infinite tree here. And we think of the sequence as determining choices, whether to go left or right at each stage. Okay, so the way I have drawn this, the tree can't go on for too long, but let's assume that it does go on forever. Okay, so it goes on here. Things will have to get shorter, faster to do that. Okay, and I think of this branch as 0 and this branch as 1, and then this branch as 0 and 1, and 0 and 1. And the infinite sequence tells us where we end up in the boundary. This boundary is an important set called the Canter set. You'll see various descriptions of these. Okay, with the metric we are going to give. Often the descriptions you see are a bit different. You could do this for any finite set, and you could have different finite sets at different levels, or even in the different branches if you want some variety. But here we have this set, and so given this, what we want to say is 2 points are close. Well, how do we look at the 2 points? They go together for a while. Maybe I have this blue path, and then it goes here, and then goes this way. And on the other hand, the purple path goes this way and diverges immediately. The orange paths even started off in a different direction. And once they diverge, we don't care about them. And finally, the gray path went along 2 steps and only then diverged. And we want to see how many steps they go along, and the longer they stay together, the closer they are. Okay, so to define this distance, we can define things in the following way. We define first a quantity, so let delta some quantity of an bn. Now this is a maximum, but it's possibly infinity. So it's the maximum of all j in n, or maybe I'll say, okay, j in n, such that for all I less than or equal to j, ai equals bi. Okay, so I look at how long these two things stay together. This could be a natural number, or they could stay together for all time, which is infinity. And now we define the distance between an and bn as 2 to the power of minus delta of a and bn. Well, we could take any other base actually. I could take e to the power of if I want, it makes no difference. Okay, with the understanding that if this is infinity, then 2 to the minus infinity is 0, and that is the natural extension where we have this. So theorem is D is a metric. And indeed we'll see it's a little more than a metric. That is the ultra term defined here. Okay, now the first condition is by construction. Okay, so D of an bn, this is 0 if and only if this is not a finite quantity delta of an bn is infinity, which means by definition this is equivalent to ai equals bi for all I, which is equivalent to an equals bn. Okay, so here we are. So this first condition is clear, but we had to define things carefully for that. But the second one is the one of the, as usual, obvious. Symmetry is obvious. But the third is more interesting. It's true, not difficult, but it's interesting. So what do we have to show? We have to show the distance. So what we have to show is that the distance between AN and CN is less than or equal to the sum of these two distances between AN and BN, and the distance between BN and CN. Okay. Now this looks complicated. It's 2 to the minus delta. How do we control this in terms of delta? It may look alarming that we have to look at logs and so on. But in fact, it's quite easy because delta has actually quite a strong property. Let's see what that is. Okay, so delta is the first place where AN and so delta of A and CN is the first place where AN and CN diverge. Okay, and so suppose the delta of A and BN is 6. That is, AN and BN are together for 6 steps. And what about BN and CN? Maybe they're together for 4 steps and then they diverge. Then it's clear that for 4 steps, the first 4 steps, AN, BN and CN are all together. Okay, and that would mean that AN and CN are also together for 4 steps. So what is this? Here we are saying, we are claiming the following relation between these deltas. So claim is that delta of AN and CN, how long they're together, is greater than or equal to minimum of delta of AN and BN and delta of BN and CN. And once you recognize this fact, it's really quite easy to prove. Okay, so the definition has been written out that way. For all I is less than or equal to j, AI is greater than or equal to BI. I want to show this is true. Okay, so we show, okay, let me write out the definition. Okay, so it's perhaps worth a fresh page and copying the definition. So with some room to work, here's the definition. Delta of A and Bn was the maximum of j such that this happens, and we want to show this is greater than or equal to this, but so since this is the maximum of some values, we show, let's call this guy mu. Okay, we show mu belongs to this set j in n such that for all I is less than or equal to j, AI equals CI. It's the set corresponding to this. That is, in other words, for all I less than or equal to mu, which is the minimum of these, mu, we have AI equals CI. But, so mu is the minimum of these two quantities, but what we know is mu is less than or equal to delta of A and Bn. Okay, so I is less than or equal to mu implies I is less than or equal to delta of A and Bn, and this implies that I is delta of A and Bn, and so this implies that we have this condition true. Okay, which is the condition in delta, namely AI equals BI. Okay, so similarly, I is less than or equal to mu implies that BI equals CI. Therefore, I is less than or equal to mu implies AI equals BI equals CI as claimed. Okay, so thus, so this is what we had claimed. Okay, so this proves the lemma. Now that we have the lemma, the theorem is easy. Okay, so theorem is in fact, I'll write it as a lemma, it will become clear. So now remember the distance. So remember the distance of whatever quantity is 2 to the minus this quantity. So monotonicity gets reversed, and what we have is distance between an and cn is less than or equal to maximum of two distances. Distance between an and bn and the distance between bn and cn. Okay, so here we are. But of course, we know that the lemma is saying this. So this is immediate from the previous one. And this is less than or equal to sum of the distances, this plus this distance, the appropriate distances. And something with this property is called an ultrametric. In definition, d from x cross x to x, not to x, to r greater than or equal to 0, to non-negative numbers, is called an ultrametric. If for all x, y, z, if, well, it's a metric, which really means 1 and 2 of a metric, because the 3 will follow from this, and distance, and for all x, y, z in the space x, distance between x, z is less than or equal to not just the sum of the other distances, but larger of the other distances. A distance between x, y and distance between y, z. So ultrametrics are certainly metrics. They just satisfy the triangle inequality in an extra strong form. Here we have defined an ultrametric on a set of sequences, and the limit, this is a metric space. It sort of keeps breaking up, and what you get is a famous object called a Canter set, the most common description of which is a little different from this, but this description is nice in many ways. In particular, it's really very symmetric. It shows you the Canter set you can flip at all stages.